Continuing with chapter 12, we're going to talk about the second idea, which is to randomize. The idea behind randomizing is that it allows us to use a sample to represent the overall population, because if we randomize, we can just take one small taste of the population, and that should be representative of the entire population. So what it really does is that it protects us from the influences of all the features of our population, even ones that we may not have thought about. And by features, I mean like race, demographic, gender, age, those type of things. It makes sure that on average, our sample will look like the rest of the population. So why not just make the sample look like the population? So make sure that we sample rich and poor and male and female. We sample all different ages. We sample people who are married, divorced, single. We make sure we hit all of the different demographics, all of the different races, people who have kids, people who don't. Why can't we just hand pick everything and make sure that it works? There's too many different characteristics and important traits that we may end up leaving out. There's going to be some that we haven't even thought of, and by randomizing, we don't have to think of them, because randomizing will take care of that for us. Even if we could end up thinking of all of them, we still wouldn't be able to get our sample to match all of these characteristics, especially not in the proportion that they occur. Randomizing protects us from bias. That's the most important part of it. Because remember, if we have bias, we have to throw everything out. And randomizing protects us from having to do that. It makes it possible for us to draw inferences and make decisions and come to conclusions about the population. So, for example, out of a company's database of 3.5 million customers, so this company has 3.5 million customers, we took two samples. Both had a sample size of 8,000, and then we analyzed those two different samples. Again, these samples were taken at random. So in the first sample, the average age was 61.4 years, whereas in the second sample, it was 61.2. The percent that are of the customers that are white are approximately the same. The percent that are female are approximately the same. The number of kids people have, again, the same. The income bracket, the wealth bracket, whether or not they're a homeowner. No, they're not exactly the same, but they are very close, and we wouldn't expect them to be the same. This is an example of sampling error, where we have variation from sample to sample. Same population, two different samples of the same sample size, produce very similar results. Not exactly the same, but similar. And that's because we randomize. By randomizing, we end up getting what the actualities are. The third idea is about the sample size. So, how large does the sample size need to be? If it's too small, then you're not going to get enough information. But if it's too big, it might be hard to actually analyze all of that data. So you might think that we need a large percentage or fraction of the population, but it is actually the number of people surveyed that matters. Not the proportion, but the number itself. Think of our soup example. So if you're tasting the soup to decide how it tastes, if it tastes good or if it's missing something, you're going to stir all the soup around, okay, because you're going to randomize that pot of soup. You're going to stir it around to make sure that all the flavors are together, and then you're going to dip your spoon in and take a bite. One bite might be enough to tell you what the soup tastes like. Maybe you might need two, and that's okay, but you don't have to eat all of the soup. You don't need to eat 10% of the soup or a quarter of the soup. You just need a few bites. That's kind of how the sample size works. It's not the percentage, it's not a fraction, you don't need to eat the whole pot. You just need a couple of bites, and it might just be the number of spoonfuls that really make up how much you need to figure out how the overall population of the soup tastes. Continuing to talk about the sample size. A random sample of 100 students in a college will represent the student body just as well as 100 voters represents all the people that can vote in the US. So, going back to the soup example, if you're making soup for a family of 4, or you're making soup for all of the freshmen that are at Western, you have 2 different size pots. 1 spoonful or 3 or 4 spoonfuls of soup will tell you how the soup tastes, whether it's for the sample that you're making at home for the family of 4, or if you're making in the industrial-sized kitchen at Western's campus. In both cases, you don't need to eat a ton of it to know if it tastes good. It's the same principle here. Those 100 students can tell you how the whole student body feels, just as much as those 100 voters can tell you how the entire population feels. So again, the fraction of the population that you've sampled doesn't matter. It's the sample size itself that is important. For a survey that tries to find the portion of the population that fall into a category, you are going to usually need at least a few hundred respondents to say anything precise enough to be useful. So if you are dealing with the entire population of the US, 100 probably won't cut it. You might need 1,000. But 1,000 was a lot easier to get a hold of than 100,000. And 1,000 might tell you just as much information as that 100,000. So again, you don't need a huge sample, it just has to represent the population. Does a census make sense? Well, first of all, it's helpful to know what a census is. So a census is when the entire population is included in the sample. So you have asked everybody. So tomorrow in class, if I were to ask every single one of you what your favorite color is, I just did a census of AP statistics because I asked all of you. And in that situation, a census does make sense. But most of the time, it really doesn't. It may appear to give the best information, but there are a number of reasons why it actually is not. So it can be difficult to complete a census. Some individuals are difficult to locate or hard to measure, which can end up costing a lot. Populations also rarely stand still. People are born and die all the time. They move in and out of state, they move in and out of a country. So being able to ask everybody can be really difficult to do. And taking a census can be more complex than sampling. So a census requires a team effort and a lot of money. You're going to have to send out mailers. Then you're going to have follow-up phone calls. Then you're going to have people go door to door to the people who have not responded yet. The homeless end up being a big issue because you don't know if you've counted them. You might overcount them or undercount them. College students are often counted twice because when you go to college you have a temporary address and then you have a permanent address. So a lot of times you're counted at your permanent address, but then you're also counted at the apartment that you're renting or house or wherever you are in college. So a census, they can be very difficult to do. So often you're going to want to do a sample instead of doing a census. Populations and parameters. Models are used in mathematics to represent reality. Parameters are the key numbers in those models. A parameter that is part of a model for a population is called a population parameter. We use data to estimate population parameters. So any summary found from the data is a statistic. The statistics that estimate population parameters are called sample statistics. So when you collect data and you analyze it, you are calculating sample statistics. These sample statistics are then used to model population parameters. Simple random samples. A simple random sample, which is abbreviated in SRS, is where a combination of people have an equal chance of being selected. So yesterday in class, when I was selecting people for Name That Bias, I did a simple random sample. All of you had a number, and you were all equally likely to be selected. We first need to decide where the sample will come from. That's our sampling frame. So yesterday, our sampling frame was our AP Statistics class. That was our list of individuals from which our sample is drawn. So I drew my sample of 3 students at a time from my 17 AP Stat students. Another example would be if we were to draw a random sample of college students. We might pick at random from a list of full-time students. We would have to define the frame first. So by defining the frame, we're saying that we're only looking at full-time students. So would that mean that we are looking at part-time? Probably not. Would transfer students be included, or are we going to talk about look at only students that started their freshman year? What about students that will be transferring out at the end of the semester? Are we going to count them? So you have to define your frame. Who are you looking at? Who are you interested in? Once we have a sampling frame, we need a way to pick the students at random. The easiest way, again, is what we did in class yesterday, is to just number everyone and use random selection. So, for example, we want to select 5 students from a class of 80. Each student will be given a number from 00 to 79, and then we get a sequence of random numbers from a list. Or, on your calculator, you could calculate 5 random numbers from 00 to 79, but you would have to ignore repeats. But using our list, we end up with 5, 16, 62, 93, 5, 77, and 48. We have to throw out the 93 and one of the 5s, because you can't have the same person twice, and 93 doesn't exist. So then our 5 students would be the students that are numbered 5, 16, 62, 77, and 48. Again, this is what we did in class when I numbered you from 1 to 17. Samples drawn at random generally differ from another. So again, this is going back to that sampling error. Again, those differences are not really an error and are more likely to be called sampling variability. This is the amount of variability between samples, and it's an indicator for the amount of variation in the population. So if you have a larger variation from sample to sample, that's going to tell you that your population probably has a pretty large variation. If you have a small variation from sample to sample, that's going to tell you that your population has less variability. That is it for today's lesson. I hope you guys have a good night, and I'll see you tomorrow.